tired. Seems like no class on Wednesday. No class on Wednesday. Okay. Great. Thanks. All right. Good afternoon. Okay, so a couple of announcements. Let me just go there. Remember, homework is due today, so that's important. Midterm next week, Wednesday, 7 p.m., 105 North Gate. We will have a review session. I will be 99% of the chances going to be here at 6 o'clock on Tuesday. So like we did last time, exactly the same type of mode. So there's some old exams on the website. Make sure to have a look at them. It's always useful to look at what kind of questions you might expect. But again, what I'll do at the review session is go to some of the old exams and answer open questions. Then project phase 2, phase 1 is done. We're probably going to have get them graded as soon as possible. Somewhere next week I would like to go to this. So let me tell you a little bit what phase 2 is going to look like. It's going to start, I'm going to try to post it early next week, probably Monday-ish, Tuesday-ish or something like that. So the first step was really kind of straightforward. Well, it was not straightforward, it was a lot of work, but fairly straightforward in terms of the topology. The topology was basically given to you. You didn't have that many choices. Now I'm going to ask you to start thinking about optimization. And trying to take the design and restructure it whatever way you want to meet a certain set of goals, a certain set of specs. Okay, so there's a number of different directions we can go, and the way I'm going to organize it is I'm going to let you sign up for 3 possible options. You're going to have to pick a goal, and they can be different, which is going to be creating some different type of solutions, obviously. Number 1 approach is A, is minimize delay. Power doesn't matter. I want to get this as fast as possible. Okay. Obviously, you should have the same function. The input-output behavior should not change, but the delay should be minimized under whatever conditions. Okay. That's 1. Number 2 is suppose you can increase the delay. So from the first phase, we'll tell you what the normal maximum worst case delays would be, right? You figure that out. So you know what the worst case delay over your first topology. Suppose I can increase the delay with 5%. Okay? Minimize power. I give you some slack. It gives you some slack in the overall design, and use that slack as well as topology improvements to minimize power. And then the other one is the reverse. If I can increase the power with a certain percentage, power plus 5%, minimize delay. So the difference between A and C is that in A, I'm not power limited. In C, I'm going to be power limited. I give you the power budget that you get from your design right now, and you get 5% extra. Okay? So these are the 3 groups, and what I'm going to do is you're going to have to sign up. Each of you are going to have to sign up, and I would like to get some kind of an even distribution of the different groups over those different targets. Okay? As I said, everything's free game. You can change the... Well, not everything. The register cells remain fixed. We're not going to mess around with those. But you can redesign the other cell. You can definitely change the topology, the way you combine things together, how you hook all your cells together. All of this is free game. You might go for dynamic. You might go for a new logic style like adiabatic or something like that. Yes?
Is the power increase of 5% including the register cells, or is it just...
Well, the register cells remain fixed, right?
Okay, so it's only of the other components.
That is correct. That is correct. Of the core. Okay. And what I'm going to give you for the power analysis is going to be slightly different vector. Power is going to be based, what I think right now is you take your filter and you apply a triangle input wave. So you start with everything 0. Then let's say this is 64. You get 8, 16, 32, 64, 32, 16, 8, back to 0. That's kind of the pattern we're going to use to analyze power. Okay? But feel creative. There's a lot of things you can do with this structure, as you probably have realized already. The way I connect the adders together, the way I play around with where the how I massage the critical path, what type of adders to use, because the adder that we have used so far was clearly built for minimizing carry. But if you look at your structure, minimizing carry might not be the only goal. Actually, you look at critical path, actually might go to some sum paths as well. Maybe you want to use a different adder cell. And as I said, if you want to do dynamic, feel free to do so. So this is where inspiration happens. This phase is going to be purely based on, I'm not going to expect layout. What I really need at the end of this phase is your new topology and the transistor diagrams of your cells with some sizing of your transistors. But no clear design yet, no extraction of layout and so on and so forth. That's going to basically be reserved for the last phase. Okay? So I truly hope that you're going to attack this from a high-level perspective. Don't go into running SPICE 100 times in a row at very fast rate, randomly generating transistor sizes and see which one comes out the best way. A, number one, is going to take way too long, and B, the chances are that you're going to miss the right solutions when you do so. It's really cleverness that's going to pay this time around. Okay? Is that clear? Any questions? You need some more handouts? There's some more over there. We can pass them along. So, questions, uncertainties? Well, we'll see. We'll post it, and then can we talk more about it on Wednesday again in class. We're going to discuss this a bit more in detail. Oh, there's no class on Wednesday. Sorry, Friday. Okay? Good. If no question, what we're going to do now is slowly but surely step away from logic. And we're going to start putting things a little bit more together. So going away from purely combinational logic and start thinking about sequential logic. Adding registers, flip-flops, latches, all those good things that really make a complete circuit. But before doing so, actually, it's worthwhile to spend some more time on power. We haven't really done that yet. We have talked about power analysis for the inverter, but we really haven't spent much time of how to do power analysis of more complex structures. Even though a lot of you have learned already a lot about it while doing the project phase 1. You see that power analysis is obviously not an obvious thing. So let's revisit power briefly. Remember the inversion? The inverter case, this is, the power of a particular node in the network. Right? So the energy dissipated at a node in the network, the dynamic power, is equal to the capacitance on that node times VDD squared times the clock frequency or the repetition rate. And then a very important factor, which is this alpha 0 to 1, the probability that for a clock transition, I will have a 0 to 1 transition on that node. Right? And those probabilities, if obviously, one way to do power, what people very often did when they didn't care too much about power, said, capacitance is proportional to area. So if I have a bigger chip, I'm going to have more power. They basically said, well, it's CL VDD squared F. So you take the total capacitance, you multiply VDD squared times multiply by F. But that doesn't really make sense because you can be actually dramatically off if you don't take this probability into account. There's actually a lot of nodes in the network, in the logic, that actually don't switch very often. It's a rare event that they switch. Think about it, they have a 10-input NAND gate. Right? The chances that I have a 0 to 1 transition are going to be fairly small. Because you look at an AND gate, you look at 10 input, that's 2 to the 10, that's a truth table of 10,000 lines. There's only one line that is a 1. And all the other ones are 0. So the probability to go from 0 to 1 is quite small if you look at a random input patterning. So you see that those gates won't switch very often. Okay? And as a result of that, switching activity is, in most chips, is actually quite small. Not all those capacitors are going back and forth all the time. Now, that's where the challenge now comes. Okay, I can figure out the capacitance, right? Capacitance is easy. You can extract it. We know how to do capacitance now. Well, it's not easy to some work, but we can have a computer program that tells you exactly at every node what the capacitance on that node is going to be on the average. VDD we know, F we know. How do you estimate this alpha 0 to 1? This is all a result, these are all probabilities. And this transition activity is really a function of, I can manipulate this in many different ways. The type of logic function, for instance, as I'll show you in a minute, different logic functions will establish different transition behavior. The logic style, remember static versus dynamic, I already discussed. Dynamic switches more often than static because I always pre-charge it, and every time it's a 0, I basically discharge it. So this logic, dynamic logic typically switches has higher power than static. It's also a function of the signal statistics. Right? If I have an input waveform where there's not much happening, like for instance, I have a filter, let's say take a little filter of your project, and I apply a very tiny little sinusoidal input. Very tiny. It only switches a couple of bits. Most of the MSBs of your filter will never do anything. Right? So on the other hand, when I apply a large waveform that goes back and forth real quickly, a lot of activity will happen. You will see a lot more switching activity. So the input waveforms have a big impact on the overall power dissipation. And then there's the other factor which is called the inter-signal correlation. This is all probabilities. If things are random, right, if you have two random signals, you will have a lot of signal activity. However, if the signals tend to be correlated with each other, they tend to move together, you will see that the activity will go down. So all those things play. And then there's the other factor is also, again, the timing dependent. This is static. You can look at just your circuit and figure these things out. You have also dynamic or timing dependent components. What those are like, for instance, is that things like glitches. I'll tell you a little bit more about glitches in a minute. Glitches are dynamic effects, timing-based effects. I have a logic structure and I apply an input, and there might be nodes that kind of waffle for a while. Waffling nodes. They go up, and then they change their mind. They go down again, and they might change their mind again, and they go up again, and finally figure out what they want to do. That can happen. So all these glitches, this back and forth, obviously, is charging and discharging capacitor is a waste. It's purely a function of the timing of your network, as we will show in a minute. And then again, signal statistics and correlations will play. But in this case, it's not inter-signal correlations, but it's temporal correlation of the same signal. You might have a signal that basically has subsequent samples might be very similar or might be very different. Let's say, first example, I have a slow sine wave that I apply. Subsequent samples of that sine wave, if I sample it quite rapidly, will be very similar. Not much activity between two samples. On the other hand, if I have a pure random number, it can go back and forth between all the values very rapidly. So these are also temporal effects. So let me explain a little bit, first of all, why the choice of a gate has an impact. This is something which we can derive quite easily. If you have a truth table, right? Here's a NOR gate. That's a truth table of my NOR gate. Let's assume now for a second that I know the signal probabilities of the inputs. I know that A and B have a 50-50 chance of being basically equal to 1. Let's assume that. That's already an assumption about my input signal that I'm making. Now, if both of those have a 50% chance, then every row in this column has the same probability, right? The probability that I will have 0, 0 is going to be 1/4. Just 1/2 times 1/2 is 1/4. Same thing here, 1/2, 1/4, 1/4. Every row has the same probability of being happening. Okay. Now, if that's the case, then what's the probability of having the 0 to 1 transition? Well, it's the probability that I have a 0, and the probability that the next value is going to be a 1. Now, what's the probability of having a 0? If all those lines have the same probability, it's 3/4. Right, there's 3 zeros in this, so 3 out of 4 chances the output is going to be a 0. Okay? The probability of having a 1 is 1/4. So now the probability of having a 0 to 1 transition is the probability that I have a 0, and that the next one is going to be a 1. So that's 3/4 times 1/4 gives you 3/16. So that's the transition probability, assuming that A and B have basically equal probability of being A 0 to 1 or 1. Okay? So if the input switch every cycle. So 3/16 is the activity of an OR gate. Now, if I will do an AND gate, I will get exactly the same results. I'm not sure if I have an AND gate here. Yeah, I have an AND gate here. It's just the opposite. Probability of a 1 is 3/4. The probability of a 0 is 1/4 times 3/4 is 3/16. No difference. Okay? So then the NOR gates typically have similar type of dynamic switching behavior. Now think about an XOR. If you think about an XOR, you see that the probability of a 1 and a 0 is equal. Right? If you look at the output, there's two versions that have 0, two versions that's 1. So the probability of having a 0 is 1/2. The probability of a 1 is 1/2. So the product of the two is 1/4. That's equal to 4/16. Right? Yeah, 4/16. So it's a little bit higher than what an AND gate is. Now let's think a little bit about that for two inputs. So what's going to happen if we start increasing the number of inputs? The fan-in. What's going to happen with our probabilities? Let's think about it first for the XOR. What do you think is going to happen? Suppose now I'm doubling the number of inputs. I make it a 4-input XOR gate. What will your transition probability be looking like? Any idea? Will it go up? Will it go down? Think about it. The transition probability is the probability that I have a 0 times the probability that the next one is going to be a 1. If I take a 4-input XOR, what would the truth table be looking like? Yes. Remains the same. One of the nice properties of an XOR, well, nice or not nice, I don't know, you can argue about this, is that the number of zeros and number of ones is always going to be the same. Right? A odd number of inputs of one input basically gives you a 1, an even number gives you a 0. Okay? Now think about an AND gate, or an OR gate, or an AND gate, or an OR gate. Any one of those. What's going to happen there? Will the transition probability go up or down? I think I already told you. Anybody who thinks it's going to go up? Transition probability. Who thinks it's going to? You think it's going to go up? Kind of waffling on it. Who thinks it's going to stay even? Who thinks it's going to go down? Who thinks nothing? Okay, good. All right, at least one. Now, actually, the downs are definitely right, because if you think about it, let's go back to this previous picture here. If I know, let's say you take a 2-input NAND gate, if I do a 4-input NAND gate, it's going to have everything is going to be ones, one single 0. So the probability of having a 0 is getting very small. And you look at the product, we'll see that asymptotically, we'll see that the probability of transition, which starts at 316, you increase the fan out, is going to go asymptotically to 0. Big NAND gates or big NOR gates don't switch very often. Think about, let's say, a very good example of where this happens is in the decoder of a memory. We haven't talked about this yet, but a decoder of a memory is a whole row of very large fan-in NAND or NOR gates. And the decoder typically doesn't switch very often much. There's a very low activity type of functionality. Okay? Now, this is assuming that PA and PB are equal to 1/2. I can easily rewrite these equations also to be valuable for every possible input pattern. And I'm not sure if I've done this. We have discussed this before. Let me just generalize this a little bit. Can I get the overhead camera, please? So, let's now think again about an AND gate. Let's take an AND gate. Okay, and I would like to compute now the transition probability. But now, instead of assuming that the inputs A and B have 50-50 chance of being 0 and 1, let's give them some different probabilities. So what's the probability of, let's say, assume that PA is equal to the probability that A is equal to 1. Okay, and PB is the probability that B is equal to 1. Okay? Now, what is the probability that the output of an AND gate is going to be 1, given those numbers? If you have an AND gate, when is the output going to be 1? Well, it's when A is equal to 1 and B is equal to 1. So let's call this PZ. PZ equal to 1 is going to be equal to PA times PB. Right? That's kind of just simple logic we're basically performing. Now, if we want to compute the switching probability, we also have to know the probability that Z is equal to 0. Well, obviously, it's either 0 or 1, and the sum has to be equal to 1, so this is going to be equal to 1 minus PA times PB. Okay? Now, the probability of a 0 to 1 transition at Z is equal to the probability to have a 0, which is 1 minus PA times PB times PA PB. Bingo. So I have generalized this equation now, and if I know the probabilities of the inputs, I can compute the transition probability at the output. And I can do this for XOR gates, I can do this for NOR gates, NAND gates, and all those type of things. And obviously you would expect that if I would plug in my numbers for 1/2, this is 1/4 times 1 minus 1/4 is 3/4, multiply that's 3/16. Our previous result is confirmed. Shows that this equation is correct. Okay? So I can generalize that, and I know, could say, well, gee, the way I'm going to do a complex logic block. Suppose now I have something that has an XOR gate, and I want to compute transition probabilities. All right, suppose I have this logic function. So what could I do? If I know the probabilities at the inputs here, what I can do is just move from the inputs to the output and start computing the probabilities. I know here, for instance, A, B, C, D, I know their probabilities. That's the input. That's my signals that I have. Based on this, I can compute the probabilities having a 1 or a 0 at the output here. Once I know that, I can compute the next stage. So I can compute basically step by step, walking to the network from the input to the output. I can compute all the probabilities of having a 0 or a 1. Okay? And once I have that, then I can compute the transition probabilities, add them all together, multiply with the capacitance, and I'm done. Sounds easy, right? Have you tried to do this for your project? You will see it's not that easy. There's a little caveats. There's 2 caveats that are very important. Number 1, which is not a problem for the project. The project, you didn't have that problem in there. But very often what we do is most sequential logic is what the output of this thing goes into a register, and this register goes back into the inputs. Now you see that the probability of A is not known. It's basically a function of the network, and it feeds back. I have a loop. So you cannot really work from the beginning to the end because you have to iterate over it a bunch of times. And you might do that, and that's taking some time, but you can do that. Right? You iterate over it, and finally you find some probability. But in your project, you had another problem. It's things like that. What I do very often, let's say I might have logic, an OR gate, an AND gate, and then this comes together. And then you have another gate, but this gate might also be a function. I'm just inventing something here. If you look at this, this signal here, X, propagates to here and through here. So both inputs of this AND gate are a function of X, right, indirectly. Now, this whole analysis I've done here is assuming that all my signals are statistically non-correlated. I only can do this forward-moving, assuming that all my probabilities are independent. You've heard about probability somewhere, right? 126, for those of you who have been in the communication space. Others, I think discrete, what is it? What class is that? Discrete math course, CS 70. They do some stuff like that over there. So this thing only works when the probabilities are independent, which are not. These are actually, in this case, you can see that the probabilities of those things are going to be connected to each other. They're not independent. And that basically blows the whole thing up to the smithereens and makes your life a lot harder. You can do it, but it becomes a lot harder. So I mentioned, let's come back to that in a minute. I just want to mention, when we talked about dynamic gates, remember, the probability of a power dissipation function of a dynamic gate is when the output is going to be a 0, not a 0 to 1. Every time I have a 0, I'm going to consume power. If I basically have a 1, I don't consume any power at all. Right, the best thing for dynamic logic is that all outputs stay 1 all the time, and nothing ever happens. Okay? So it's somewhat different computation, and we've done that. I already analyzed that. Oh, by the way, you do dual rail domino, the ones we discussed last class. It's a cool idea, differential logic, differential pull-down networks. From a power perspective, not a very good idea. Because what I'm doing here is guaranteeing that there's always going to be a switching event every clock cycle. Because now I'm differential, You pre-charge both outputs to 1, you're sure that at every clock cycle, one of the two is going to go to 0. Either the left or the right one, but your switching probability now becomes equal to 1 for this type of thing. So dual rail domino is good for performance. It's not very healthy if you're concerned about power. Anything which is differential, as you can imagine, is not very good power, because you double your activity, basically. You're going to have more efforts going on. The other one you have to worry about is the clock. And that's true for dynamic logic. That's definitely a case. The clock is the worst case type of signal I already mentioned before. It switches always, and it consumes about 25 to 50% of the power in most complex processor chips. So the way we're going to do this is, and that's a very important one, it's kind of a little sidetrack. I'm not going to talk more about that. But for instance, if you have a big chip, and certain parts of the chip don't do anything. Let's say I'm not using the multiplier, for instance, for a while. Like I have a very complex data pod with a bunch of multipliers and ALUs, and I don't use a multiplier. It's a good idea to disconnect the clock from that multiplier. Even though if I keep all my inputs constant, but if that clock keeps going up and down and up and down, all the fan-out capacitance of that clock is going up and down. So here I have this big multiplier. If you look at it from a clock signal perspective out, there's a big fan-out capacitance hanging in here. Definitely if it's a dynamic one, all those pre-charge and evaluate transistors hang off from there. So it's a good idea to disconnect that when you don't use the block. And the way you disconnect it is typically using a gate, which just enable or disable the clock. And this way this thing doesn't switch anymore. Very, very simple. But basically, remember when you want to do power, even though in the project we're not going to turn things off, so it won't help you very much in the project. Okay, so let's come back to this problem. As I said, analyzing power. We could do this very simple trick, move from the inputs to the outputs, and get the whole thing analyzed, and we're all done. But as I said, it doesn't work very well for sequential circuit, and it doesn't work very well for this kind of case where you have, for instance, this reconvergent fan-out, as you can see. It's a very simple example, OR gate followed by an AND gate. You see signal X is the output Z here is a function of X and B. Now we could do our analysis, okay, the probability that Z is going to switch. Okay, if I would do my simple analysis, X is the probability of X equal to 1 is going to be equal to 1 minus PA times PB. Right? Very simple. It's an AND gate, it's an OR gate, so the probability of having a 1, so let's call it PX, is 1 minus PA minus PB. Right? 3/4 of the case, if it's an OR gate, 3/4 of the case, you're going to have a 0. Okay? Then you can say PZ will be equal to, now I have PX, is PX times PB. Right? It's an AND gate. The AND gate is going to be a 1 when X is equals to 1 and B is equal to 1. So now what PZ should look like is equal, I can plug it in, is 1 minus PA PB times PB. And let's assume that this is 50-50. That's basically 1/4 times 1/2. You would say 1/8. Now, evaluate this logic function. Z is equal to A plus B and B is equal to 1. If you basically simplify this equation, you see that B and B is always, it's basically AB plus BB. So it's AB plus BB, basically it's always a 1 condition in this case. This thing never switches if you evaluate it. At least that's what I think. Let's say AB plus B, yeah, so it's A plus 1 times B basically what you get, which is 1. So this logic gate never switches. So this thing is definitely wrong. This PZ equals 1/8 doesn't make any sense. Okay? So there's an error somewhere. If I look at my logic function, this whole logic network doesn't do anything, while this at the output says exactly would switch at 1/8 of that the probability of having a 1 is 1/8. So what was wrong here is that we didn't do this
that we ignore the fact that x and b are basically not independent of each other, but they are dependent. And the probability that z is equal to 1 is equal to the probability that it's an AND gate, is the probability that b is equal to 1 times the probability that x equal to 1 given the fact that b is equal to 1. So that's this dependency here. What is the probability of x equal 1 given the fact that b is equal to 1? That's where our conditional dependencies come in. And then you work it out, and you basically will figure out, if you do this analysis, you will see that this is equal to 1. Okay? So you can just work this out with your conditional dependency type of analysis. Now you can imagine I can do this for a simple gate. But if I now have your complex adder network, as you did in the project, and you try to compute basically all these conditional dependencies for the whole network, you're going to be toast really rapidly. Because there's a lot of reconvergent fanning, there's a lot of input, you get very long equations, it basically goes up indeed. Yes? What? One on B and B, right? Okay. Yeah, it's equal. 1 second here. AB plus B. Yeah, it's B. So it's equal to the probability that you have B. So let me just check this. You're right. You're right. Still doesn't change the condition here. In this case, you would get a 1/2 switching probability. Right. You're right. You're right. But bottom line is, of this whole story, is that you have to basically do this conditional analysis. And that's very complex. So it works for 3 gates. It works for 2 gates. It doesn't work if you have 100 gates, 1,000 gates. People have tried to build programs who do this automatically, but they're kind of iffy and not very accurate. So the only way to really do this is to take your data patterns with the right input thing and do a high-level simulation. You don't have to simulate this at transistor level. If I can simulate this thing at logic level, I plot my patterns and I just simulate the ones and the zeros through the thing. I don't care timing, I don't care size of transistors or what logic style you use, basically. The only thing I really care about is how often does this node change, given my logic topology. So from pure logic, high-level VHDL simulation, I can figure out all those switching probabilities. I extract my capacitances, I combine the two together, and I basically get my result. So that's the way typically power analysis is done. High-level simulation can be done real quick. Feed the patterns through it, figure out transition probabilities at every node, multiply that with the capacitance, and we have our dynamic power. Okay? And in a sense, if you want to do power analysis in a project and you want to do power minimization, doing some style of analysis like this is probably going to be the better choice. Okay? Oh, it was this particular example here. I got confused between the two. All right. Now, here's an interesting thing. Looks like a figure with some things have disappeared. Are they in the printout? There's nothing there either? They disappeared, huh? Thanks to the Mac. I did this on a Mac and then moved it to a PC, and Macs occasionally tend to eat stuff, at least figures and so on and so forth. I think this is as far as I look, I have to look, I think it's 2 AND gates come together, but I'm not 100% sure. It doesn't really matter. As I mentioned, if you look at logic and you do, let's say you do a simulation, you probably did the simulation of your large logic function, right? And you look at the waveforms and you probably notice that some of the waveforms in your adder array kind of do multiple transitions. During one clock cycle, you have a node that initially might go high and then go low again, might go high again. Okay? We call that a glitch. Right? It's from a pure functionality perspective that 1 to 0 transition doesn't do anything, because what really counts is value that you get at the end of the clock cycle. Right? Some people also call them dynamic hazards. Now, You might think, why? Obviously, from a power perspective, this is not something which is very desirable, right? If you think about it, any one of those transitions basically is wasting energy. So we would like to eliminate them. But before you can eliminate it, you have to understand why glitches happen. What is the main reason that a glitch can occur in a certain logic function or logic block? And that's why I'm using this example. I'm going to have to try to understand here is A, B is 1, 0. Let's try to see, okay? I think it's AND gates, but I might be wrong. So let's assume that initially you have the following inputs. A, B, C is 1, 0, 1. Okay? If 1 is 0, this X should be 0, and this is 0. So I think it's AND gates, at least from deduction. So far, so good. It matches what I would expect. So you start at time 0, 1, 0, 1, 0. X is 0, Z is 0. Then I change my inputs, my primary inputs from 1, this goes to 0, and this goes to 0 simultaneously. What's happening? Well, if this goes to 0, 0, there goes my theory. What? It could be a NOR function. Probably is. Yeah, because it didn't work for, at least it worked for initially, but then from the time I basically look at my second transition, it doesn't work anymore. So suppose I put a NOR gate here. This node here, 0, 0, this is going to go to 1. Right? But at the same time, so at this particular time here, we change. With a certain delay, X is going to go to 1. Remember this delay. Okay? Now, what does this AND gate see here at that period of time? I'm not sure if it's an AND gate, but it doesn't really matter. It sees that it sees one of its inputs changing, but the other input, X, will change, but actually is changing a little bit later. So initially, it sees here, while I'm 0, this is now going to 1. This remains at 0. It goes to 1. I think it's another NOR gate. So, but then, a little bit later, after one delay, the X signal changes as well. And basically, now we get here a 1, and we get a 0 on this side. So the thing goes back to 0. So temporarily, we had, both of them basically go to X is equals C. C is 0. X is 1. Yeah, you go back to 0. So what really happened here? The fact that you have this glitch here, you have this temporary type of transition. The reason this happened is the following thing, is that my X signal is actually changing later. You have a gate, the last gate here, where the two inputs change at variable times, or different times. So initially, when the first input changes, it still sees the other input. And then a little bit later, it says, oh, the other input has changed, and I have to recompute myself. Okay? Main reason then for the glitching is that if you look at any gate in a network, it might be an input type of thing, multiple inputs, you will see that there will be temporal differences, different arrival times of the inputs at that particular gate. Okay? If all inputs would change exactly at the same time, we would never have a glitch. Things would basically march nicely forward. Okay? So, but that's rarely the case. For instance, let's say here's a simple example. It's a chain of NAND gates, whole chain where initially all of those are 1, 0, 1, 0, 1, 0, and so on and so forth. So all the outputs of my structure are initially going to be equal to 1. And then what I'm doing is simultaneously change all the second inputs of the NAND gates to 1. And the expected result now is that there should be a 1, 0, 1, 0, 1, 0 pattern. But what you see is that initially, all the outputs start to actually change downwards. Because they haven't seen, they see still a 1 here. You change this to 1, 1 to 1. Oh, NAND gate says 1, 1. I have to go to 0. So all these NAND gates in the whole chain all start to go down. But then these changes start to ripple through the network, slowly but surely, and say, hey, no, it's not the way. Actually, the input is different. So some of the nodes start to go back up. They change their mind. And the deeper you go into the chain, the more the glitching effect becomes, because it has more time to propagate through the system. Okay? So glitching is purely a result of the fact that you have long chains. You have basically, if you look at this gate here, one input is a primary input, changed at the time of the clock. The other input has to propagate through a long, long chain. Just as we would see, for instance, in adders. If you have a ripple adder, that's exactly what you see, right? All the primary inputs are applied immediately, and the carry kind of ripples through. And before the carry arrives, you already might start going in another direction for the sum output, for instance, or for the carry output. So that's a typical glitching problem. Now, what's the way to get around this? Well, the way to get around this is avoid to have any gate in the system where you have very big differentiation between input arrival times. Now remember, we have done exactly the type of thing. Remember the carry select adder that we talked about a while back? And how we could make it logarithmic, not square root out of n. What we did is I looked at the arrival times of the different phases in the carry chain, and looked at this, hey, this circuit here, this multiplexer, has one input which is already sitting there and is ready, and has to wait for the other one to arrive. So what we did is make every block gradually larger, so that we balance the propagation delay to each one of those multiplexers. So that was an example of a topological type of change which help us to eliminate not only glitches but also improve performance. Let me give you another example. It's not going to be perfectly correct logically, but suppose I have something like this. This goes here, the same example I just had. This is a chain. Now, if I could do something like this instead of having a chain, I create a tree network. You see, in this case, my inputs arrive at the first gates. They propagate to the middle level. They arrive at the same time over there. Then they go to the next stage. They arrive finally over there as well. So you see that all the arrival times at the different phases in this network will be similar. So tree structures like, for instance, those carry look-ahead adders we looked at, very often have a smaller amount of glitching. Okay? So balancing paths through the network is very important if you want to get rid of glitching efforts. So what they often do actually in logic synthesis, which is kind of interesting, if you take synopsis and you go feed it through the synthesis path, if they see a very long unbalanced path, they actually might inject inverters in there just to balance the paths out a little bit more. That's something that some of those logic synthesis help to do to remove basically glitching effects. Okay? But at the same time, you have to be careful because you also increase the capacity if I put more inverters in there. But that's a different story. So it's a trade-off game. Okay? So that's the glitching thing. It's if you're not careful, like with big logical structures like multipliers, actually glitching could become a sizable chunk of your power dissipation. It could be 30%, 40%. So it's worth looking at it, because it might actually, just basically some small topological optimizations can improve your network substantially. Okay? So, good. That's kind of the basic analysis. Remember, what a basic message is, look first of all at the conditionals, try to compute switching activities, and then add some temporal effects, which is basically glitching. Glitching is a purely the result of temporal effects, of timing effects. Now, if you want to reduce power, it's already helpful if you start thinking about the project. What should you do? How can we reduce power in the design? Right, you have, let's say, you've done your filter, and now I'm saying, okay, I'm going to give you 5% more extra time. I'm going to allow you to spend a little bit more time. What can you do to reduce power dissipation? Well, option number one, obviously, is, and that's something you definitely should consider, is, can I use this to reduce the supply voltage, for instance? If I reduce the supply voltage, my circuit is going to be slower, but I get my VDD square savings. So reducing the supply is always a good idea. Run it at the minimum supply is a good trick. The second thing that you have to be aware of is that very often in design, there's a lot of waste. If you don't think very carefully, people oversize transistors, right? You want to be fast, you want to be macho, you make big transistors. Big transistors, more capacitance, is a waste of power. So reducing waste is kind of an obvious thing, but people violate it all the time. Most circuits actually waste power left and right and so on and so forth. These days it's getting better because people are getting very much aware about power. But in the past, wasting power was normal. They didn't care. As I might have mentioned already, this example of the first Pentium processor that was released, the first Intel Pentium was around 1990 or something like that. It was kind of funny. They're kind of embarrassing for Intel, but that processor was using the most amount of power when it was executing knobs. No operations. Which was ridiculous, right? You don't do anything. You just feed knobs through the chain, and that's when you really were peaking on power. So they randomly, everything was flipping back and forth. So they created a lot of random effects. They figured that out quite rapidly. The next generation, they did a much better job on that. But it was clearly an example of waste. So clock gating, turning off clocks when you don't need them, eliminating glitches, logic restructuring to basically eliminate glitches or basically make your logic simpler. All those things are very useful. The other thing is, as I already mentioned, don't be macho. It sounds good. I say, well, gee, I can clock this thing at 2 gigahertz. If, however, your application only requires 500 megahertz, you're wasting, right? So make your circuit just fast enough. Being too fast is not, basically, nobody is going to give you a bonus for that. And so, well, hey, by the way, I'm going to run this thing so fast. It doesn't matter if it's video compression or video thing. If you meet the video rate, you're fine, right? So power is equal to VDD squared. If I'm basically too fast, lower the supply voltage a little bit. For example, you can actually make it even slower by sometimes doing two things in parallel. There's a couple of games you can play to basically reduce power. And then finally, there's transistor sizing. So suppose I've done all the things that I wanted to do. I've done all those tricks. I minimized waste. I limited all this stuff I didn't have to worry about. So what else can I do? Well, here's an important way of looking at power. Remember, and I think that's an important message I've already given you a couple of times, is that nothing comes for free. Typically in design, it's all about trade-off. If I want to make something faster, I'm going to typically need bigger transistors. It's going to cost me energy. So suppose now that I have this beautiful program that takes your design and says, I'm going to design an adder. And automatically you generate all possible adders in the world. Right? And size all the transistors, randomly put all the transistor size in there. What you're going to get is something like this curve here. You're going to get a whole bunch of dots. Every one of those adders will be a dot in this space. So on one axis here, I have the energy. And on the other one, you have the performance. Okay? What you will notice is that you fill in the whole space. You will see it always gets that same shape. You will see that there's going to be a set of designs that are sitting on this curve here, which we will call the Pareto optimal curve, where there's no design that's getting any better than that. So let's say for this performance, let's say that's the speed I need to get. This design here is going to be a minimum energy design. All these other designs are suboptimal. Right? So from an overall design perspective, this is where I want to be. I want to be on this curve. You're basically going to size your transistors, choose your supply voltage, choose your thresholds, and so on and so forth, that basically in such a way that you're going to meet that, or basically that you're going to be located on this Pareto optimal curve. So that's an interesting thing. This is a trade-off game. Depending upon the performance, I basically can play around with the energy. If I need a very high performance, you will see that the energy is going to go up. For very low performance, I can actually save in energy. So moving on this curve based on your performance type of requirements is going to be important. And what your job as a designer is to make sure that you're on that curve. Being here is a really bad idea because you're suboptimal. There's better designs out there. Now, obviously generating all designs automatically, basically all possible designs, is somewhat of a task. But it's worthwhile in your exploration. When you do your design of your adder and things like that, it's probably worthwhile to say, okay, let's try to figure out how I can size my transistor. Maybe automatically. There's actually optimization programs that help you to find those curves. That say, okay, here's where a Pareto optimal curve is, and then for you, it's basically your job to find out what design that meets that particular requirement. But it's always good to keep that thing in mind. Design is always this trade-off game in the energy delay space. That's where we're playing. Trading off delay for energy and vice versa. And we know there's always an optimal curve that's out there. Now, I can do this for, let's say, for a single adder. Let's say I take a ripple adder, and I can define a curve like that. Right? Now, a ripple adder is very simple. Probably is going to be good from an energy perspective, right? From an energy perspective, it's going to be better, but from a performance perspective, it's not going to be very good. Well, if you do look at a, let's say, a look-ahead structure, very good on performance, but obviously on an energetic perspective, it's not going to be very good. So you will get a curve which is going to be more like this. So if you look in energy delay space, every adder will have its own optimal energy delay time. So if I'm basically sitting and I'm interested really in low performance, you see that the ripple adder is going to be better. If you're at high performance, actually, you're going to be better off with the look-ahead structure. So now by putting and superimposing some of those energy delay curves on top of each other, I can figure out which structure is the best for what performance region. Now, this takes a lot of tools and things like that. I don't expect you to, in the project, to basically generate complete curves like this, but it's good to keep it in mind that there's always this energy delay trade-off. And by using different alternatives, I can shape the way the curves look like. Okay? There's another thing that basically is very apparent from this thing here. It's that being extreme never pays off. Let's say if you look at this curve here, I might go for the maximum possible performance. I'm going to be here. Right? And I'm going to really push hard, big transistors, I do everything in the book to get the best possible performance. You see that the cost in energy is huge because this curve is almost flat here. So just getting a very small improvement in performance is going to, let's say, from going from here to here, is going to cost you dramatically in energy. Right? So being at the edge basically means that, yeah, I can get 1% improvement in performance, but it costs me 30% in energy. Same thing here. This is also very flat. Minimizing energy. I say, oh, I'm going to basically squeeze out another femtojoule. Might actually cost you 30% in performance or 40% in performance. So being here typically is a bad idea. I say back off a little bit. Maybe go here or go here, which gets you better performance, and it costs you maybe only 1% in energy or 1% in performance. So it's a much better design if you can kind of back off a little bit from those extremes. That's an important thing to remember as well. It's nice to know what the extreme is, but typically from a pure cost-benefit analysis, it's not a very good idea. Okay, this is kind of repeating what I just said. I have two designs. I have adder 1, I have adder 2. I can look at my Pareto optimal curves and I can say, okay, in this region, adder 2 is the better. If you go to high performance, adder 1 is the better one. And now I can compose them and I get the global optimum curve for those two together, or 3 together, or 4 together, or 5 together. And the beautiful thing, this is true for gates, it's true for adders. I can compare microprocessors that way. Well, let's say I have a tool, again, a magic tool, that generates all possible microprocessors for me with different structures. 8-bit, 16-bit, more registers, less registers, Harvard, von Neumann, all this kind of good stuff you learn in the computer architecture courses. Right? Same thing. I can, for every one of those processes over a set of benchmarks, I can generate all those points. And in the end, you plot performance versus energy, and what you will see emerging? Exactly one of those Pareto optimal curves. Exactly the same thing. So this holds for every layer of your design architecture. And I think it's something that people didn't realize for a long time. They said, we're going to minimize energy. No, you're always going to minimize energy within a performance type of perspective and vice versa. And that's why this vision really helps. Wow, my slides these days turn to go automatically. It's cool. Okay. Any questions on power? Any remarks? Cool. So I think it's going to be important, right? That this is an important part of the project, trying to evaluate how your decisions are being made and how you can help save power through that fairly complex design, right? You get quite a bit of adder cells in there. Trying to think through what optimization is going to be good, where it's going to drive you, is going to be very important. Okay? All right. Having said that, let's go. This is the end of chapter 6. We're now going to move to chapter 7. A very important one as well, because now we're going to actually start adding the missing link. It's nice to do combinational logic, but if your circuit doesn't remember anything, it's kind of not a very interesting circuit. So let's go to sequential logic. And I think I've shown you this slide before. The difference between combinational logic and sequential logic is very simple. In a combinational logic block is the outputs are always a direct function of the inputs precisely at that point in time. Right? They're only a function of the current inputs. If I know the inputs, I can tell you what the output is at any point in time. In the combinational logic block, we have feedback. Some of the outputs, or intermediate outputs, are being stored and fed back into the structure at the input. And as a result, now you can see that the output at any time t is going to be a function of the inputs at that time t, but also of the previous inputs. It has memory. Right? For instance, if you look at your FIR filter, it's a 5-step FIR filter. We know it's going to remember at most 5 time slots. Right? You put something in your delay chain, it goes through, and after 5 clock cycles, it disappears. That's why it's called a finite impulse response filter. It has a memory 5 levels deep, because there's no real feedback in that thing. It's only feed forward. Okay? So, but you already see that the register files, or the registers in that filter, help you to remember previous values of the inputs. Okay? Now, in order to do so, we have to have that thing that can store a value and remember it into the next clock cycle. Okay? Which is called a flip-flop, or a register, or a latch, depending on what you're basically talking about. Now, this is called sequential logic. Why do we call it sequential logic? Well, sequential means sequencing. It comes from the same thing, sequence. Now, we're not going to do things all instantaneously, but there's now going to be a sequence of events happening. Okay? Now, sequencing is important. Right? Suppose if I wouldn't have sequencing, if I have no way of ordering, and there's different ways of doing ordering in a thing, but if it wouldn't have ordering, now suppose, let's say, I take a logic block like this. I take an input, a combinational logic, and I take the output and I feed it right into the input here. Now, I see a waveform coming out. How can I interpret this waveform? I don't know. Right? If I look at this waveform, it's a pure analog waveform. And you see at some point in time it goes from 0 to 1, and then it goes from 1 to 0. Now, what is the real value of this waveform in the digital space? I don't know. I have no clue. Because this could be 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, or this could be 0, 1, 0. I don't know. Because I don't know. The typical thing about digital logic is that you create the values at discrete times. But if I don't have a way of creating discrete times, if I don't have that sequencing, I have no clue what the actual values are. Where do I sample my result? So that's the first thing that we have to. With this logic, you don't know, right? It's a continuous thing. I apply some waveform in here, and some waveform going to come out, but I don't cannot interpret, I don't have a way of interpreting this in the digital space. So I'm going to have something that creates a time base. And the time base typically is going to be your clock. But it doesn't have to be a clock. Right? If I do a self-time type of thing, remember the completion thing that I mentioned? It could be saying, hey, I'm done with my computation, go on to the next one. If I have something that helps me to create order, like this comes before that, this comes before that, I'm already a lot better. But that's what clocks do. It's a very simple way of creating a time base. So that's one reason. The other thing that is important is that if I don't have a time base, so you take a single, as what I said is you take a simple signal, and I don't really know exactly at what time I have to sample. It's even worse if I have multiple signals, right? Suppose I have multiple inputs here, and one arrives earlier than the other one. How do you align them with respect to each other? Right? Now I have two independent waveforms, and I don't know exactly when they're both going to be valid. So again, should it be 1, 0? Is this 1, 1? Or is this what? We don't really know. So again, a time base helps us to align the different signals together in the chip. Basically tell you, at this point in time, both of them are valid. And we can go on to the next step. So it's very important, because if we don't have that ordering in digital circuits, we have a big problem. And that's what registers do, and that's what clocks do. Registers store the values, and clocks tell you at what time the value, the data value, is going to be valid. Okay? Now, if we go to CS150, I think most of you took CS150. You probably learned something about flip-flops. I hope they still teach that. And latches. So if I think about memory elements, there's two kind of things you have to remember about memory elements. There's two styles, and one of the two styles of memory elements. It's one thing, and the other thing that you have to remember is that there's two ways of storing information in digital circuitry. Two very fundamentally different ways for us to remember something. Let's first talk about the different styles of registers or storage elements that we have. Something which is called a latch, and something we call a register or a flip-flop. Both of them are used interchangeably. Okay? So what's the difference between the two? Well, a latch is kind of a little gate. It's a device that has an input which is called D and an output called Q. Why D and Q? Nobody knows. The reasons are lost in history. But the output of a flip-flop is always called Q, for one reason or another. Way, way back, somebody says Q sounds like a good number, so let's pick Q, and since then it has always been Q. D is the D input or the data input. That I can understand that. And you have a third input, which is the clock. Something that provides that sequencing, that ordering effect that we talked about. Okay? Now what the latch does is the following thing. The clock really is nothing else than a gating function. If the clock is low, the output Q will remain constant. We'll just remember its old value. Okay? However, when the clock is high, then the input will just propagate to the output. Okay? So you have two modes. Clock is low, we hold the value at the output. We just store the value and keep holding it. When the clock is high, we feed the input to the output. Let me just show a simple example here. So this is my D input. Okay? Clock is low, we're just going to remember the previous value. We'll hold the value, assume that this is 0. Okay? So we hold the value, nothing changes. D changes at the input, but since the clock is still low, nothing happens at the output. We keep on holding this 0 here. Then suddenly the clock goes high. At that point in time, the output D will propagate to the output. So at that point in time, you see that Q will go high. And then the clock goes low again. Means that we're going to store and hold this value. Even though one stays high, clock goes high again. You see, we're in transparent mode here. And you see that once again, the D output will basically propagate right away to the output. So it's like a gate. It's either, you can, if I look at it from a a very primitive fashion, this looks to me like something like this. When the clock is when the clock is low, the switch is open, and we just retain the old value. They say that this capacitor is a way to store the old value. When we close the switch, input goes right to the output. That's really what a latch is. Okay? Now, a register is different, or a flip-flop. It's a by the way, we call this level sensitive. Okay, because level sensitive, because the fact that the input, when the clock is high, we basically get the input level goes right to the output. The register, on the other hand, is something which is called edge-triggered. And you have two types of trigger, but let's assume that we take a positive edge-triggered flip-flop. I'll come back to that in a minute. What it says is the following thing. The output of the flip-flop will only change on the rising edge of the clock. Every time the clock goes up, we're going to sample the input and put it on the output. Okay? So you can see here that you have your Q. D goes high, nothing happens. And then my clock goes high. I'm taking the value of D at that point in time, which is 1, and put it on Q. Clock goes low. With the other sampling event here, it's still 1, so it stays 1. Till finally this goes 0, nothing happens. Still, once again, we have a positive event on the clock, and this goes to 0. So the only events are happening at edges of the clock. Okay? Infinitely fast type of functionality. This is called a positive edge-triggered flip-flop because it works on the positive edge of the clock. I could also have a negative on, something that basically works on the low-going transition of the clock. You can choose. Doesn't make a difference, it's just an inverter. Right? That's the only difference I really have. Now, both of those elements are very useful and have been basically, designers play with both of them, edge-triggered flip-flops and latches. Latches, again, are a little bit more complex. This is, again, for the high-performance designer. If you take a standard cell library and you do automatic synthesis, all flip-flops will be edge-triggered. Makes life a lot easier. You don't have to worry about some nasty things that we'll show you in a minute. Okay, so this shows the same thing. This is a latch. A latch, basically, when the clock is high, you see you have your inputs here. When the clock is low, the output remains constant. Independent of what's happening with the input might go up and down and up and down. However, when the clock is high, you can see that the output follows directly what the input does. This is called a positive latch. You can also invert it. Who cares? Just the opposite. When the clock is low, it's active. It doesn't really matter. It's the same thing. It's just that what's the polarity of the clock that we're basically acting on. Okay? Now, before going to the timing effect here, let me just mention one thing. Now, let's actually go forward on this here. Now, remember gates. What do we care about in a gate in terms of timing? So you have the logic functionality is clear, right? You have latches, you have registers. Let's think a little bit about the timing characteristics. For a gate, we basically worry about propagation delay, right? You have a gate. Propagation delay is the delay between an input change to an output change. Right? We take the 50% point, and it can vary between the different inputs. Okay? Latches are a little bit different because we have, or flip-flops are a little bit different, because now we have a D input, a Q output, but we have a third input signal, which is this clock thing. So now, what is the delay of a flip-flop? Or what is the delay of a latch? That's an important thing to know, right? Because it's part of the overall circuitry. I have to be able to find a timing definition of the key properties of a latch or a flip-flop. So things are a little bit more complex. Think about a register. What is the delay of a register? Well, remember, a register or a flip-flop changes only when you have a rising edge. Let's say positive, you have a rising edge on the clock, and then we will see a change at the output. We sample the input and we put it on the output, right? That's the idea of a register or a flip-flop. So what I really care about from a delay perspective is how long does it take me between, let's say, I have a rising edge on my clock, this goes up, how long will it take me before the input appears at the output? Okay? So we have a rising edge on the input, and you will see that if, let's say, this is equal to, say that the input is high, this is low, initially, a little bit later, this will go up, and go to 1. It will sample the input and send it to the output. So you take your 50% points, and that's the delay of your register. Same like before. Take the 50% point of the clock, 50% point on the output of the register, and that's your delay of your register. This we tend to call the C to Q delay. For apparent reasons, C stands for clock, Q is a Q output, C to Q delay is a delay between the C input and the Q output. Okay? Now, latches are a little bit more complex because the behavior can be depending upon the mode. Obviously, we still have the C to Q delay. So when the clock goes high, the latch is going to go into transparent mode. And it's going to take a while before the input is going to propagate to the output. So we again have a C to Q delay, just like we have in a register. But there's a second delay we have. Suppose your latch is in transparent mode, which means input propagates to output. Obviously, there's also going to be some circuitry in between those two. So if I now change, while my clock is high, so you have your clock is high, if I now change the input from 0 to 1, it's going to take me, so this is the clock, this is D, this is Q. It will take me some time before Q will change to 1 as well, because it has to propagate from here, the D, to the Q output. This is the 50% point again. This is what we call the D to Q delay, obviously. The delay between the data input and the Q output. Now, it's obvious that this doesn't matter here because this never happens. The only changes are allowed on the edges of the clock. There's no transparent mode in the register. Okay? Is that clear? So remember, first thing, that a register now has 2 delays. Well, a latch has 2 delays, a register has 1. But we're not done yet. There's some other things we have to basically worry about with registers and latches. Things you might have heard about again when you were talking about in 150. I think you probably talked about this. Suppose, let's say, I take a register, right, or a flip-flop. Apply a clock edge right here. Now, suppose I do the following. Remember, the register is going to latch, is going to basically sample the input at the rising edge of that clock. Suppose now that my input changes exactly at the same time. Right? So you're sampling, and you sample exactly at the same time as the input. What's going to be the output look like? Is it going to be the previous value, or is it going to be the new value? Okay? That's pretty hard to know. We don't know. It's undeterminist. Actually, it turns out that for a register to work, it is a good idea to keep the data stable, and actually it's a necessity, that your data doesn't change. So you basically have your data change back and forth, and then you're going to latch it here, or basically sample it here at the rising edge of this clock. It is essential that we keep the data stable a little bit before that edge event. Okay? It's a necessity. Otherwise, your register might do weird stuff. This is what we call the setup time. So you have to ensure that your data is set up and stable before I can apply that clock event. Okay? So setup times are important because you violate them, you might end up with some weird stuff in your register, which you don't know what it is. Okay? So setup times. Now, the same thing holds also in the other direction. Suppose, again, I take a edge, I basically apply my edge event, my clock edge, and I say, okay, I'm done. I'm going to remove the data right away afterwards. I'm going to turn the data, start changing the data right after my clock basically go to the 50% point. Chances are, again, that the data that's going to be in your register can be kind of corrupted. So it's a good idea, in general, to keep the data stable a little bit after the clock event as well. Actually, for a lot of designs, it's almost a necessity to do so. This is called the hold time. You have to hold the data, so you have to set it up first, take some time, apply a clock edge, and then you go hold the data stable for a little bit longer. for a particular period of time, which is the hold time, and then you basically can start changing it again. Okay? So setup and hold times are very important properties of a flip-flop as well. And violations against those can be not very healthy for you. So if you look at most companies, if you basically do complex design with a lot of designers, there's actually going to be automatic tools in there that basically check and verify if you basically don't violate setup and hold time. It's one of the biggest violations that can make timing go wrong in the design, is the violation of this setup and hold time thing. Now we'll come back to that later, but it's important that you remember that a flip-flop, logic gate is quite simple: rise time, fall time, and the delay, propagation delay. That's all you have to remember. Flip-flops have a little bit more: C to Q, D to Q, hold time, and setup times. Okay, from a timing perspective. Okay, so I have just a couple more minutes before going into more detail now on how I would design this register and flip-flops. I just want to mention that if you look at storage, again, as I said, we have two styles of elements: latches, registers. We also have two fundamentally different ways of storing data in digital designs, CMOS designs. First approach is the following one. Can we switch to the overhead camera, please? There we go. All right. One way of storing something is something we already know. If I have a capacitor, if I want to store a 1, I can charge up this capacitor, leave it there. So I charge it up. And if I want to get a 0, I discharge it. And if I disconnect this capacitor and it will remember the previous value, it is a memory. Right? So capacitors are perfect memory elements and quite cheap, because you want it or not, we have capacitors everywhere in a logic design. So one way of storing things is just putting charge in the capacitor and then later on measure what you have on this capacitor. For instance, using an inverter or something like that, I can measure what was on the capacitor. Okay? Now obviously this has some problems, because anytime I basically connect something like a transistor here to put the charge on there or a thing, we will have leakage. So this is something that is, you charge is only going to be there for a certain amount of time, and then you lose the value. For instance, this is the way DRAMs work. DRAMs, dynamic RAM, is purely based on storing charge on the capacitor. Right? Like we did for dynamic logic, we call this dynamic latches or registers. And just like we had in logic, there's also a static version. And the static version of a register is based on a very simple concept. Basic core of any static latch is going to be this, or register. That's what it is. That's my storage element. If I take two inverters and I connect them back to back, I create something that remembers a value. For instance, if I can put a 1 here, this is going to be a 0, this is going to be a 1, this is going to remember the same thing. Similarly, I can have a 0 here, a 1 here, bingo. Okay? So a cross-coupling of two inverters becomes a memory element. And if I don't remove the supply voltage from this thing, it will remember it forever. Obviously, when I remove the supply voltage, it will go away. So you might need some other memories that remember things forever, even if the supply voltage, but that's another thing. So, but this idea is a very interesting thing. What you get when you connect, and I'll show you this in the next lecture, obviously every inverter has a voltage transfer characteristic, right? Something like this. So this is inverter 1. If I now connect inverter 2, and I'll come back to that in a second, I get this. And I connect them back to back, you can see that I have a number of points that are stable points, operation points. Actually, I have 3 stable operation points. A 1, a 0, and something we don't like. Something we don't like, well, obviously, if I connect two inverters back to back, there is a probability that this is equal to Vm and this is equal to Vm, the switching point. That's a perfectly legit solution. Right? You put both of them in the middle at half VDD, and you'll see that this is a perfectly legit point. So you have 1, 0, 0, 1, and VM, VM. Now, the nice thing about this thing here is what it's called metastable. It's not a stable operation point. A single electron coming by will switch this out of this position and move it either to 1 position or a 0 position. So this, in reality, is a bistable element. And that's very interesting. It's either a 1 position or a 0 position. I will remember it. So we'll come back on that in the beginning of next lecture. So we'll see you, first of all, Tuesday, 6 o'clock for review. And then on Wednesday, 7 o'clock for the midterm. And I'll post some more information on the website regarding the midterm. It's going to be here. The midterm is 105 North Gate. An hour and a half, whatever. If you ask many